something called C sub delta over 2 delta. So for the next, I don't know how long I have a lecture, I'm actually going to keep much content. Partly because there's sometimes gotten wrong. John Gravy does this calculation in 3 different ways, and the answer, it gets one answer twice and the third answer once. And so by majority vote, he takes the answer he gets twice. And anyway, I'm doing it partly because it's possibly the wrong answer. And actually, when you're comparing these 2-point functions with observation, there's a meaning to the normalization. And so, why not? I want to understand, why people get different answers. Okay, so anyway, and this C delta is some, let's see, we need to find some solution to this problem. I don't even know it's on the computer. I need to get it on page. Okay, so far, it's probably my equation, so my equation, but anyway, the main thing for the budget purposes is you're on the boundary, you get this funny coordinate C, the delta, and that's just right. And this is not it, so I'm going to put another normalization constant C sub O into there, and later on tell you what the standard convention is for C sub O. Okay, and so when you combine that with that, the 2-point function, so you plug this in there, take the limit, and the 2-point function. Oh, I forgot this. Okay, and the data, when I first wrote down the Klein-Gordon equation, I included for later reference an overall normalization constant in the action, and so I similarly need an overall normalization constant here. So now the main part, of course, is guaranteed by symmetry. This is just a check that we haven't done anything wrong, and so far the answer has no interest. The only interest in normalization, and so far the normalization is just a bunch of convention. So all we've organized is a check, a warm-up. Of course, you could now extend. We're not going to talk about 3 and higher point functions. So now, if you wanted to extend it to the 3-point function, the 4-point function, things that start to have more obvious physical meaning. Again, you just have the boundary z equals 0, and you have some 4-point function of phi's, and you take those all to the boundary, and in the bulk, you have some scalar field, and maybe they exchange your graviton, maybe there's some Klein-Gordon term, and so you'd be summing over all of the, so you find the rest of the bulk, and then taking the limit. But we're not going to do. It's interesting, and it's been done very fine. We're not going to do any of that. We're going to focus actually on 2-point functions. Well, because that's your goal. We're going to focus on 2-point functions. It will keep us busy enough, and it's interesting. Yes. In ordinary field theory, this formula is very reminiscent of the LHC formula. The LHC, I guess, I'm continuing around here. Yeah, good. And in ordinary field theory, that formula actually doesn't make sense as an operating statement. It only makes sense when you make your elements are taken between wave vectors or wave vectors. So is there any analog of that here? So, now, I've never studied axiomatic field theory. And that's not what you're asking about, right? I mean, we're supposed to interpret these things as some kind of distribution. That's not the question you're really asking. If you do this research, and you don't put in that research, you're not going to very function. I don't know, but maybe something you're thinking of that I've forgotten. I mean, the thing which is more analogous in my mind to LHC formulas than something else, which I might talk about this in another direction, but there's a question which I find a lot, which is if you take a look where the ADS space is very big and nearly flat, then in the interior we should be able to talk about string physics and the things like the Zion amplitude, and we should be able to recover them by sending in focused wave packets from the boundary and derive in that form something like an LHC theorem. And that of course does require wave packets, but that's more analogous to what I think you're asking about. But this is a direction that I'm probably not going to go into because it's orthogonal to go ahead on. Yeah. So yes. Just symmetry. So field theory is the boundary. Field theory is a small number of axioms, conformal invariance, operator quad expansion, associativity, and so conformal invariance is guaranteed by construction. The operator quad expansion again is just insertion of a complete set of states, so it's kind of guaranteed by construction, and associativity similarly is just insertion of a complete set of states in different channels. So I think it's the psychology that this definition satisfies. I don't know if it's your question, but if it was, that's the point that I'd like to make. That I think it's almost a psychology that if you have a theory of gravity, any theory of gravity in the bulk, this construction, then you do something that satisfies the axioms of field theory. Is that your question? There's 5 exchanges in the 2 particles. There's 5 exchanges in that. Why are there 2 particles in the boundary? Well, there's no particles in the boundary. There's only 1 particle in the boundary. One particle in the bulk. Right. You're not doing anything change in the boundary. You just have a machine that generates a correlators in the boundary, and in some cases we also correlators come apart on this specific project. So there's nothing else you could do that, in the last lecture I talked about what you can bang on this duality, and actually let me show you this question, because it's actually, it's one of the ways you can bang on duality coupling. So let me tell you, I don't have your question, but I'm going to talk about something like that in the last lecture. Okay, now we're going to stop, but I want to relate this duality, this version of the dictionary to the version in terms of generating functions. And as a first step, we can consider a mixed 2-point function where we keep one field in the bulk, but we move one to the boundary. So a 2-point function between an operator in the bulk and one is to move to the boundary. And if you take that limit, then it just becomes keeping my conventional normalization constant in the right places. you integrate this and calculate its weight, you find that as it goes to the boundary, the leading behavior is indeed a delta function. Well, first of all, there's z to the z minus delta, that's the total weight in that function, times the delta of x minus x prime, and then actually this constant was pulled out to the just canceled out, and so you're left with this, everything else is there. Good. And, sorry. No, sorry, that's right. So, before we talk about conventions, let's talk about what this looks like. So what we're saying is that if we put an operator in the CFT and then probe it in the bulk, this is exactly the non-normalizable bulk, the bulk of the mode that was previously fixed to 0. So this statement here about operator is equivalent to the statement that an operator in the boundary sort of has the effect of turning on the previously fixed non-normalizable mode with a delta function coefficient. That's actually the way the dictionary is usually stated. And in fact, now the convention is that the operator is normalized, so this is 1, so that an operator turns on this mode with unit coefficient. And so that's the convention that we'll take. So you can go back now and simplify all the equations by using that convention. By the way, it's a good point too that it's convenient. Now that I've had my diatribe and done my calculation, which is equally valid in Euclidean or Lorentzian, now I'm going to actually fix to a Euclidean metric simply because in Lorentzian metric there's an I here. And so I have to carry around a bunch of I's in the equation, and nobody does. They always do these calculations in Euclidean signature. Now we're in Euclidean signature, and this is one. So now that if we insert into the CFT, if we insert into the exact expectation value, now we're going to take this idea and make a generating functional out of it. Then that has the effect that in the bulk, in ADX, the function alpha, the alpha of x, which was previously set to 0, is now set to j of x. So the quantized mode, the quantum mode, the mode which is fluctuating, is still the normalizable mode, but the non-normalizable mode has been now set to a non-zero fixed value. And so now we can say the dictionary this way, the way you probably were thinking about it, that the expectation value in the CFT of this operator, so this generating, is equal to the path integral of the bulk with alpha fixed to this value here. Also, in the player limit, in the large n limit, the bulk theory is classical, and this is now just e to the minus x classical with the given boundary condition on the non-normalizable mode. So this is the statement of well, you can leave that that way because it's easier to think about the switching between but it's easier to think about switching between signatures down here. You have to think harder maybe about how to switch things. It's not that much harder, but you can start to get more confused, I think. Okay, so I'm going to spend a few minutes on how you actually do this calculation over here. Because again, it's at this point again that John and various other places in the literature still get two different answers, and again I want to understand why that is. So again, the action is my conventional normalization, and then CDXTD, and then just the Klein-Gordon action. But the thing is, when you evaluate the classical action, so when you extremize this, so it's a boundary condition, then it reduces the surface term, you can integrate by parts, and get the equation of motion, and all you pick up is the surface term. Actually, maybe I should write this out also in a statistical coordinate system, just to go to there, sorry. So, the equation of motion, so you can drop the bulk term, and I've actually moved the lower bound of z down to some small value epsilon rather than 0, so you kind of how factors cancel as we eventually take epsilon to 0. And so again, you can solve the classical equation of motion with this boundary condition. So you solve the classical equation of motion with this boundary condition, plug that into the action, it gets the surface term, you evaluate it, and it looks like this, except again, it has a slightly different normalization constant in front. And it's not a big deal, but it doesn't seem to affect most calculations, it's worth understanding what went wrong. And then wrong, I think there's a lot of went wrong, but there's a simple way to think about it, which is the following. This action as it stands needs the original action needs a surface term added to it. And the reason is if you vary phi, there's a bulk term in the variation and the surface term in the variation. And in order to have an action principle, you need the surface terms in the variation to vanish. When we consider all variations allowed by your boundary conditions, you need the surface terms in the variation to vanish. So in fact, the original action needs an additional surface term. There's no equations in the notes. There's no reason for me to put the ball on the board, but I want to explain the logic of it. Thinking about surface terms. So I vetted with this with him, and he approved of the logic. And the logic is, there's a lot of conditions that you might want your surface terms to satisfy. But the most important one is you need a consistent action principle, meaning that the action really is stationary, right, classical solution. And in the bulk, this means to satisfy the field equation. Again, on the boundary, it means that the boundary variation vanishes, and it doesn't for this action. When you add this particular surface term, the variation vanishes, and then when you add this into the calculation of classical action, you get the right answer. So, question? Okay, so I think good question. That is higher order in 1 over n. because the reason, in fact, that I carry this extra constant eta around is because it's of order 1 over n squared, meaning that the coupling of the bulk is order 1 over n squared. Any kind of so we've done we're just doing this graph. The back reaction would be this graph, and that's a 1 over n squared reaction. That's a homework problem. Yes. We talk about function. There is yeah. You can get it. Yeah, that's right. Yeah.
So first comes needed to cancel the obligation.
Yes. No, we just count it. There's a cross term. The whole point is that we do so there's the alpha mode that we fix, and the beta mode that still varies. And there's an alpha delta beta surface term from here, which is canceled by this. Yeah. Anyway, kind of OCD-ish point, but it's quite confusing. And one of it is quite confusing. It's not really. It is a few lectures spent 2 lectures on this, doing calculation 3 different ways. And I think the essence of it is what I just told you. Okay, so actually we're moving pretty well. So I want to do one more 2-point function. This one that has some meaning, and this one has meaning also that will segue in later lectures, in later lecturers to interesting physical calculations. I want to do the 2-point function of the energy method tensor. So the energy method tensor has dimension d. That's always true. This follows from the word entities. And so this is a scalar field, and it's dual to the fluctuations of the metric. So H we know is the dual to the fluctuation metric. If it's a scalar field, we would then say that the 2 modes go as z to the d and z to the 0. And again, that's right if we refer the metric. That's right for not the metric, but for the metric expressed in local inertial coordinates. So h u hat is h mu nu times the. Let's see how we do this. Z mu nu is like z squared, is L squared over z squared in the background, and so the d line, E mu nu hat, is the square root of that is L over z, and so h mu nu hat times into the inverse, so it's times z squared over L squared. Well, let me turn that around. H mu nu is L squared over z squared times h mu hat, and so the 2 modes of it go as z to the d minus 2 and z to the minus 2. Okay, so and this is right because in fact if you look at this, the non-normalizable mode, the one that we're going to fix, has the same scaling as the ADS metric itself. The ADS metric goes as L squared over z squared eta mu nu. And so if we can say that if we deform so this is the metric of the CFP. If we want to ask what does the CFP do if I put it in a different metric, if I change this, then this just corresponds to changing the non-normalizable mode of the bulk metric. And of course, a small change in the metric of the CFP is just equivalent to the application value of the energy method tensor. So this is just the dictionary that says considering the energy method tensor to the boundary theory is like changing the non-normalizable mode of the metric of the bulk. So it comes with a natural normalization because we can directly identify again the metric of the CFT with the limit of the metric in the bulk. Okay, so. So metrics are messy because they have indices, and sometimes they have to work, but sometimes we can be lazy, and we can be lazy because there are some components of the metric where the calculation is identical to the scalar calculation, and that's the case here, namely if we take the transverse components of the metric, so h12 with k in the 3 direction. The same as the action for a scalar field of mass 0. And so we can just import our earlier calculation. Also, this is the case, in this case, delta is z, delta plus is d, delta minus is 0, so the like surface term that I was talking about that's here is just the bulk action. So we just repeat the scalar calculation. The normalization classes, I don't want to talk about in detail here because we've already talked about, but I think I just go to the end, and in the written notes you can see more about where they all came from. So you find that the length of reduction would have the second root term. I'm sorry, this is with, of course, because it's formatted to convert it to first order form. So in fact, when I said those words to me, I was exactly wrong. The issue for me is it's not the one I wrote here, it's given talking because the invariant actually starts out in the other form. Yes, so it was a thank you. I misspoke. So another thing I want to do, another thing we're doing the same calculation again is, we were lucky in the earlier calculation because we were able to write down all of the correlation functions in position space due to the high degree of symmetry, but once you turn on temperature and fields and things, that's not going to happen, and so you're going to want to work in momentum space. So here in fact, sorry, H is not just the, H is how you look at working in momentum space. In momentum space, when you solve the field equations of the bulk, you get these characteristic vector functions. And in particular, I guess I'm now going to specialize to, I've been carrying around arbitrary D for the CFT, but I'm now going to specialize to the ADS5 theory, and this is whatever zone you was on the boundary. Okay, so the double function, and if the boundary goes, this combination goes to a constant, which we're just interpreting as the perturbation of the boundary metric. And if you go down to the horizon, in these Euclidean calculations, this double function goes to 0. If you continued it to the top space, well, you can figure out what happens. In this form of the calculation, it's always easier to think in the Euclidean case. Okay, and also, this action is... After using the equation of motion to reduce to a surface current. And if you, in order to evaluate the classical action with this solution, we need to expand out the classical solution to a few powers of z, of epsilon, which is epsilon, and keep the finite piece. So, h classical is 1, is the overall thing, times 1, and it's order k squared, z squared piece, and then there's a piece we're going to care about, which is t to the 4th log k, and I'm going to, again, write normalizations down, minus 1/16. Okay. So now, if you insert this, if you insert this classical solution into that action, you'll see the leading piece looks like it's going to come from, we square this, it's going to come from k squared epsilon squared, you differentiate 1 to a quarter epsilon, the order epsilon to the minus 3, which came from the volume originally, and so the leading term here is actually divergent, it's like epsilon to the minus 2 k squared, and I could have actually, that's not surprising because this is analytic in momentum, which means that it's a local current position space, and we're always interested in the two-point function, this finite separation. The local terms are, generally subject to convention, and so we, anyway, so if you don't care about it, you can normalize it away if you do care about it. But the first, so this log is important because it's the first non-analytic piece, the first piece which is non-local in space-time, and so when you insert that, the piece of interest is again h boundary squared, L cubed, k to the 4th log k over 16 LP cubed. And now, if we translate this into let's say 2-point function, and if we let me actually do this because it's worth seeing if everyone. So we're here in the so this is the 5-dimensional gravitational action, and so there's a 5-dimensional Planck constant that appeared there. The 5-dimensional Planck constant is descends from the 10-dimensional Planck constant by dimensional reduction, so you think of a factor of the volume of the 5-sphere, which is pi cubed L to the 5th. And so when you use, and all these concepts are in my notes, I'm not going to do them on the board, when you use the known value of the ADS radius, and you express the 10-dimensional Planck constant, and you express that in terms of the 10-dimensional Planck constant, this whole thing simplifies into something which is like this. Okay, so then we got a 2-point function, and later on, so this is the thing, once you turn on temperature, and you look at the appropriate Lorentzian retarded green function, this is the same 2-point function that you read the viscosity off of. So, I'll leave that for Don Stone. But for today, the normal, so in position space, this is 1 over x to the 8. Again, it had to be because these are dimensional operators, so their 2-point function goes to 1 over x to the 8. But the normalization is actually interesting because this particular 2-point function, in this theory, cannot depend on the Cook coupling. It's related by supersymmetry to the anomaly coefficient for the R symmetry, and so it can't be normalized. And so that means that one can calculate this coefficient, this 2-point function, in the Wiggin couple theory, the gauge theory, and the value you get is going to be the same as, none of these 23 quarter factors, are going to be the same as what you get from the gravity calculation, and indeed it is. This calculation was done by Professor coming up a few months before Maltese paper here, and they just came close to stating duality and stopped, but they really had the idea of duality in comparing these calculations. They sort of like the relationship between Poincaré and Einstein, one guy had all the equations, and the second came along and said, well, this guy. Anyway. Okay, so that's I think all I'm going to do with 2-point functions, and then what I'm going to do with the dictionary. So again, in conventional physics, they're usually just measuring 2-point functions. They pick the system in some way, and they see what happens somewhere else, a conductivity to 2-point function, and so on. And so most of the calculations are versions of this. Okay, so no questions. I'll start lecture 5. You're saying this is an object which is sort of half in one theory and half in the other. It's a, yeah. I think you have to think of both in the EDS. I think you have to think of both in the both theories. Well, it's something where I know this, I can have nothing in the both theory, but the O piece is the thing which in the both theory is the thing that is the thing which will be. So that's why I want to No, the reason I read it all was, it's really used in the book, it was auxiliary quantity to give this interpretation of, the boundary DCFT thing as harmonic perturbation of the boundary distance in the book. And by the way, let's think about this another way. We're about to use the idea. So So we're inserting this thing into the CFC. We're thinking of it as a generating functional for changing, for creating the operator color. So we also think of this as actually something that we actually perturb the CFC. We give it a different Hamiltonian. And you know, what does that mean in the book? In the CFC? Well, we can't really change the Hamiltonian of string theory. String theory of intended dimensions, Hamiltonian doesn't have free parameters. It is what it has to be. And so if we preserve the Hamiltonian of CFC, it can't be the Hamiltonian, it can't be the local physics of the gate of the book theory we're changing. The only thing we can change really is the boundary condition. So the point of that mixed object was just to develop that bit of dictionary. It's not something that has some specific physical significance in the CFC. It was derived, well, another way to derive it was from consisting of the 3-point function, because it was a 2-point function. I find that more roundabout. I think it's just a more direct statement to say you gotta see my dash, or you gotta see my descent flash, and that's just simply, that's the only criterion. Yeah.
You said the local part of the flash.
Wait, I said the local part of the local, I said that the contact term is 2-point function contains no gradient. Is that what you got for this question? That's an interesting point, because you're going to say that in this work of the Borel inference is exactly from it. It's true. Yeah, it's true. But what's also true is that the contact terms are strongly functional functions of convention, and they made a particular choice of what they mean here. So in their framework, these local contact terms seem to be meaning. That's because it's in a context where they've made a specific definition of how they're going to normalize, how they're going to define the correlator here. So my last subject then is. So we focus here on only one example, the n=4 example, that blocks the symmetry. And I there are a lot of different ways that you can bang on this, and get much more diverse examples. And the thing is, really, we can list a few goals. One goal I mentioned earlier, and Tom mentioned, is duals of the landscape. So the same construction that gives you the landscape of stabilized string vector gives you a lot of candidate solutions to start with. And so the consider solution should have CFT duals. That is, if there's a sensible quantum gravity theory in the inner space, then the dictionary automatically generates correlation functions that satisfy the axioms of field theory, and so there should be some Lagrangian that generates those correlation functions, and no one has any examples of this. The landscape vector have more complicated internal. So far, our internal spaces at the pi-sphere, the landscape vector have Calabi manifolds with fluxes and stuff. But also, there's a couple of very exciting quantitative things, but simple things that you can't do yet. One is, as I mentioned earlier, in all the known examples, the compact vector like ES5 and the AES space have the same size, same curvature radius. And there's just examples of duality in which the compact space is much smaller than the AES space, if everything really is true. So one goal is to find those. And another long-standing goal that I've had in some fifth work is that there are these non-Fermi liquids that you're going to hear more about. There's this beautiful Fermi liquid fixed point that has existed for a long time through Landau, and then there are, when you couple this to additional modes, there's some new universal fixed point that nobody understands, or everybody understands, but each of them understands it differently. And so there's some sign that there might be some useful, some job for AES-CFT duality in terms of giving a simple way to think about this fixed point. And so one of my goals for a long time has been to find AES-CFT duals. On the field theory side, you have something like the Fermi density of fermions, where you have these low energy agitations that live near the surface. So you like that. Those are two goals for, part of all I do here is develop a toolkit for more general examples of duality, and those are two goals I have defined so far. I don't think my toolkit is big enough to reach either of those goals, but it's good to have a goal you can't reach. Even bigger, if you ever reach those two goals, of course, the even bigger goal is to reach the dual construction of string theory in the Sitter space or more cosmological space times, but that can require something more than a toolkit, can require some new ideas. So also with regard to the Fermi dual, other people say this, but since I'm the first lecturer, I'll mention it. There's two approaches to constructing duals in this matter system. There's the one like what we're doing where, let's say you find some collection of the top-down approach, you find some collection of branes, which have some low-energy field theory on them, and then by using this machine, you figure out what the geometry is that describes the historic coupling. And then there's a logical approach where you just sort of postulate a geometry, and you postulate some set of fields, like a metric, of course, and one or more gauge fields, which are duals conserved currents, and some matter fields, bosons, and or fermions, which are charged. And then you simply ask, this gravitational theory gives me some field theory that has some properties. All those properties, do resemble things that we see in matter physics. And now everybody wants to know what's Lagrangian. You really want to top-down construction, but it's very valuable because what it's able to do is, given the input of some collection of operators with some dimensions, it enables you to calculate as output, the various observables in the system. So, my toolkit is directed at the top-down attempt to really start with Lagrangian, what it is, and get to a gravitational solution. Okay. So, there's kind of a long list of things. This next lecture in 15 minutes is just kind of one example after another. None of them discuss, in the course of the time in a large amount of detail. But what I want to do is work from the example we have. And the first thing you can do, even within the n=4 theory, without changing the theory at all, you can break the conformal invariance because the theory has many vacua. The CR potential. So I described how the Lagrangian descends from the tensor space Lagrangian. The CRs came from the extra components of the gauge field, and the non-abelian term in the Yang injection gives us this characteristic coming here potential, which is very for many reasons. I'll mention another interesting thing about it in the next lecture. But for now, the main point point is that it has lots of vacuum because as long as these scalar fields are n by n matrices, but as long as the matrices all commute, that is, as long as they're all diagonal on the same basis, then that's a vacuum. And it has a simple interpretation in the dual theory because these scalars in the gauge theory have the interpretation as the collective modes of the d-branes. So this corresponds to, as we take the near horizon limit, not having all of the d3 branes on top of each other, but having them, so if these are the directions sort of transverse to the d3 branes, and we're looking at them head-on, instead of having them head-on, instead of having a coincidence, pulling one or more or all of them out, so that like that. And so in the gauge theory, this is a minimum of the potential. It's actually an exact minimum of the theory, exact vacuum of the theory because of the large degree of supersymmetry. Over here in the gravity theory, you've got these parallel d3 branes, and of course these are BTS objects. These are motor charges in addition to their gravitational interactions, and because of supersymmetry, all the forces balanced, and the configuration of parallel d3 branes is stable. Now, just kind of to complete the mission, I mean, it's the simplest way to break the formal invariance, and from the point of applications, these are fundamental scalar fields, and for the most part, in the ion physics and in the matter physics, you really don't want fundamental scalars. These are a bit of an artifact that come along with the supersymmetry. And it just, I tried to make these top-down constructions of fermion microscope for a long time, and one of the problems is instabilities. Once you have the density of fermions, the theory is not supersymmetric, and your middle are protected against phase transitions. And in fact, once you break the supersymmetry, you really want the vacuum to be the original one where all of these things were coincident. You don't want these things to be out there breaking all of your symmetries. And so one of the annoyances in making a top-down fermion liquid is stabilizing the system so that the true vacuum with broken supersymmetry is the original one, and not with these scalar fields running out to some finite distance where you get to infinity. I want to use the Coulomb branch to make one more remark. I asserted, this is an aside, but I asserted that everybody asserts to you that the n equals 4 theory is the Fermi invariant, first scale invariant, and then the Fermi invariant. And for many years, people were very, working in the old days of sort of quantum graphs, people were very hard to prove this, even so as a perturbation theory. And of course, now there's a nice, elegant modern proof. I want to give the modern argument. And it uses this space of vacua. Because we got on the space of vacua, we got to some point where all of the d-branes are separated. So we had originally an SUN gauge symmetry, but this now breaks it to the individual symmetries of all of the d-branes minus clear. We always lose that one. And we can write down an effective field. So the effective energy field theory contains the diagonal components of the U1 components of the gauge field and the U1 components of the scalar where I runs from 1 to n. And so we write an effective Lagrange field, in particular the kinetic term for the gauge field. Okay. Now, if the original n equals 4 theory had a running coupling, I would have to tell you what scale I was evaluating that g at. Because the Lorentz theory is free field theory, everything is billion, and so this is one Lorentz theory, it's some number, and I'm going to tell you what number it is. And so if it ran in the original theory, this would be a function of scale in the original theory, and the only thing that sets the scale is the things that break the gauge symmetry. And so the Lorentz Lagrangian would have a kinetic term which is field dependent, but this is forbidden by n equals 4. Yes. So you're working on the question. This is the CFT. This is the CFT. This is the CFT. Right. This is the CFT on R3. On class 6. Right. So do you want to comment on how we change that? On the CFT, actually, give me 1 second. Give me 1 second. So anyway, that's really the end of the argument. That is, the high gauge supersymmetry requires the gauge kinetic term to be field dependent, which means that it can't have dependent on the energy scale. And if you n equals 2 supersymmetry, n equals 1 supersymmetry, the argument that the kinetic supersymmetry weaken, but in many cases, one can draw similar conclusions. Now, so on the free sphere, there is these scalar fields have some positive curvature coupling. This is the curvature of the free sphere. This is in the gauge theory. The conformal symmetry, in order for the theory to be conformal, there needs to be a specific coupling between the scalar fields and the curvature, so that when you put it on the free sphere, these are massive, and you need this, in fact, for the dictionary to work. Now you ask, what does it mean in the book? What does it mean in the book that the scalars are massive? Well, since it's a totally different picture. We no longer have these quantum directions in which we can stretch these d-branes. We have the free sphere that we quantize the CFT on, and if the scalar field is constant on the free sphere, means we have some spherically symmetric application of this theory. What it does mean is that we pulled out we created a point and expanded a spherical d3 brane. And in fact, the quadratic curve here exactly matches the tension of the spherical d3 brane. Now, there are cases in which this is interesting. That's actually most interesting when you got down to dimensions of the d1 branes, but anyway, that's what happens to the Coulomb branch on the free sphere.
We have it also different. There's also the other condition that we particularly might see, not related to the configuration of the Lorentz.
Oh, yeah, sorry. I'm not sure what configuration. I mean, there's deems that have not been coordinated. This is a very nice observation of Rob Myers. What it deems, in fact, is that the D3 rays pull out. They don't pull out like this. They enlarge into they become continuous third object, so they become a D5 or an N5 ring. So previously the D3 rings were just on flat 3 dimensions. This is now a 5-dimensional object, which is still stressed in those 3 dimensions times S2. And in fact, the very next subject is a perturbation of the N equals 4 theory in which exactly this happens. So thank you for your question. Yeah. So Professor Locke, there's okay, it's fine. I don't stop there and continue stuff. And remember what I told you. It's just the fact that you can. General, and I just want to very briefly give a concise summary of the field theory side of the specific duality, the N equals 4, D equals 4, ADS5 prototype duality that we're focusing on as a prototype. So the action is, well, we can concisely write the action down using dimensional reduction. So first start with D equals 10. And then the is, of course, the hemisphere under matrices, everybody's an adjoint, and you have coincident D-branes. So you just write down pretty much the simplest thing you can. That's Kali. And that is a Yang-Mills action, and an action for the, for a fermion, I'll tell you what diagram in a second. And this is just a Dirac action, a gauge action, but it happens to have supersymmetry. It has one n-dimensional supersymmetry. But now to get to the theory of Rickerson, we just dimensionally reduce. So we split xm into x mu for mu equals 0 for 3, and xm for m equals 4 up to 9. And so d10x just becomes, we just ignore the dependence of the fields on the 6 coordinates bond. So this becomes d4x. And of course, derivatives with respect to these then just are 0. They mean nothing. And you have your 10-dimensional vector potential, which separates then into a 4-dimensional vector potential. And 6 scalars from the dimensional reduction. Okay. So down in 4 dimensions, if we get more fields and more terms of the action, they all descend from the angular field strength, and you see right away that there was the original larger Lorentzian variance of the 10-dimensional theory, and we still have tests. Even the 6 dimensions we ignore them all equally, so there's still this symmetry, which acts on the 6 scalars. Similarly, the baryons, they're the smallest spinner you can have on the 10 dimensions, 16 real components, small on a vial. And if you similarly decompose these in terms of 4-dimensional spinners, they become 4 times a D equals 4 vial spinner. In particular, these transform as a spinner representation of this. Okay. So that's pretty much all one needs. Just remember the field content, the symmetries. Okay. It's also useful to think about the whole action in another way, which is starting down in 4 dimensions. If we have reason to sometimes focus on one. So the supersymmetry. The supersymmetry similarly is 16 real, which in 4 dimensions is 4 vial spinners. So that's why it's D equals 4, N equals 4. Anyway, down in 4 dimensions, it's another nice concise way to write the theory. If you focus on superfields that display one of the 4 supersymmetries, then so down in D equals 4 equals 4, any one supersymmetry notation, you have a vector multiplet. You have 3 chiral multiplets, all in the adjoint. And then, of course, the 4 spinners, one of those is a chiral multiplet, the 4th lives in the vector multiplet, and it's because we are not showing all the symmetries, they're split in this way. And then it's just the standard supersymmetric action with a superpotential, which is of the form trace. So here are 3. The cardinal superfields imply 1, 2, 3, trace of